Welcome to This Explainer. Today we're diving straight into the cutting-edge techniques making large language model inference faster, cheaper, and massively scalable. We're keeping this explainer under 6 minutes, so we're going to move fast and pack in a ton of value. Let's get right into it.
Okay, imagine buying a massive, wildly expensive GPU, only to realize that a dismal 20.4% of its memory is actually doing any work. The rest is just completely wasted by older, naive deployment systems. Absolutely brutal, right?
To fix these massive inefficiencies, we're going to journey down what I like to call the LLM efficiency stack. Our agenda today: the inference cost bottleneck, smart routing and caching, how page detention saves GPU memory, batching and disaggregated compute, and finally, scaling LLMs to the edge. Section 1. The inference cost bottleneck.
So here's the crucial point. A naive deployment inevitably leads to massive inference waste. We're talking about literally computing the exact same words multiple times, just because different users happen to ask similar questions. You're burning expensive GPU cycles on entirely redundant tasks, all while struggling with debilitating memory fragmentation. It's kind of like leaving a supercar idling in gridlock traffic. We absolutely have to be smarter about this.
Moving on to Section 2, smart routing and caching.
Think of a smart LLM router exactly like a traffic cop. Look, you really don't need a premium, massive model just to format a basic block of text. By utilizing dynamic routing strategies, you can automatically assign simple cases to cheap, lightning-fast models, strictly reserving your premium models for complex reasoning. The result? You get super low costs without sacrificing an ounce of quality.
Beyond just routing, we can completely eliminate redundant work using prefix caching for inputs and semantic caching for outputs. This lets us bypass unnecessary computation entirely. Think about it. If 1,000 users share the exact same system prompt, prefix caching means you compute it exactly once. And if a user asks a question that's already been answered, semantic caching just hands them the previous response without ever waking up the LLM.
And the financial impact here is just staggering. Take Anthropic, for example. Their cached prompt reads cost just 30 cents per million tokens, compared to $3 for fresh processing. Guys, that is a 90% discount. Honestly, if you aren't caching right now, you are literally throwing your money away.
All right, Section 3. Page detention saves GPU memory. Now let's look at traditional systems. They pre-allocate these massive, continuous chunks of memory based on a request's maximum possible length. But because the system obviously doesn't know how long an LLM's actual response is going to be, it heavily overallocates. This creates a massive graveyard of empty, totally unusable slots. This severe internal and external memory fragmentation is exactly where that terrible 20.4% utilization rate comes from.
So enter VLLM and page detention. It's this incredibly elegant solution that borrows the concept of virtual memory directly from operating systems. It allows for flexible, fine-grained sharing of memory blocks across requests. Instead of reserving one giant contiguous block up front, the memory is dynamically paged out. This practically eliminates fragmentation and allows totally different requests to efficiently share memory. It's a total game changer.
Down to Section 4, batching and disaggregated compute.
To avoid pipeline bubbles, those brief, agonizing moments of wasted idle time, continuous batching dynamically mixes the prefill and decode phases right inside the same batch. This keeps the GPU constantly crunching numbers. Instead of waiting for a whole batch to finish just to start the next one, the system continuously ejects finished requests and pulls in new ones on the fly. Building on that, using disaggregated compute, we actually physically separate the heavy reading phase from the writing phase. When a new request arrives, it's handled strictly by a dedicated pre-fill worker whose only job in the world is to process that initial prompt. Then, the second that pre-fill worker finishes reading the prompt, the computed KV cache memory is migrated, just a single time, over to an entirely separate decode worker. Finally, the decode worker takes over to actually write the answer. It generates the ongoing tokens until the request leaves the system. By isolating these fundamentally different reading and writing workloads, those decode workers can focus purely on rapidly spitting out text without getting bogged down by massive incoming prompts. This effectively eliminates GPU idle time.
And our final stop, Section 5, scaling LLMs to the edge.
Serving multiple fine-tuned, specialized models, or LoRa's, on resource-constrained edge devices like phones or drones introduces some really unique hurdles. But a new framework called Edge LoRa solves this with 3 specific innovations. It automatically routes requests to the right adapter, it smartly manages heterogeneous memory between disk and active RAM, and it batches LoRa inference to keep things blazing fast despite the limited hardware.
And this translates directly to real-world performance. Edge LoRa achieves up to a 4x boost in throughput, all while using significantly less energy than previous Edge frameworks. We're talking about juggling thousands of fine-tuned adapters on a small device without your system ever grinding to a halt. It is wild.
So, after seeing how the LLM efficiency stack intelligently optimizes everything from semantic caching all the way down to GPU page faults, you really have to ask yourself, how much money and capability is your own infrastructure leaving on the table? We covered a lot of ground in under 6 minutes today. Take these concepts, look hard at your deployments, and start reclaiming those lost resources. Thanks for joining me on this explainer, and stay curious.